So primarily what I work on is statistical software, in particular statistical software called STAN, which is used mostly for fitting complicated Bayesian models. Dan also works on STAN, but many other things too. And this paper really came about because we've been releasing all this software, and we get a lot of questions about, right, how do you use this? What's the workflow? And we didn't really have great satisfactory answers that were accessible enough to all the communities that we wanted to be using the software. And I think visualization is a really great tool for doing that, for exposing more people to how do you think about the modeling process and the implications. And so that's why we wrote this relatively simple paper, actually, but just basically to have this all in one place, like some ideas about the process of these models. And so we're going to use a quite simple example to illustrate this. But here are our other co-authors. So yeah, it's Dan and I, along with Aki Veturi, Michael Betancourt, and Andrew Gelman, who are not here, but contributed a lot to the work. And so these are the stages of the workflow that we're going to talk about here: exploratory data analysis, prior predictive checking, which is essentially what are the implications of your model, right? What does your model say even before you've fit it to data, right? If you can generate data from it, you can think about the implications of your model. Then, of course, like actually fitting the model and algorithm diagnostics and things like that. Posterior predictive checking, which is now checking the implications of your model after fitting it, right? The implications for data that it can generate. And then model comparison. And if we have time, we'll talk about things like cross-validation and how you can make visualizations about some of these things. All right, so the example, which actually, I heard Stefano mention this in his talk too, although he mentioned PM 2.5, so we chose to use this as our example. And so it's estimating particulate matter smaller than 2.5 micrometers in diameter. To give you an idea, that's like much smaller than like a human hair. And breathing this stuff in is quite deadly. It causes a lot of deaths every year. And the problem is that we only have really sparse network of like ground monitor data and mostly noisy satellite measurements. And the coverage of that is really varies across the globe. The black regions are where we have ground monitor data. So you see like mostly North America, Europe, I guess that's China, India, but we basically have few, if any, in Africa, South America, right? So we're relying a lot more on satellite data in some places than others. And then the colors here are the concentration levels, right? So it actually looks like we don't have great monitors in some of the regions where we would need them the most, right? And so to actually undertake this data analysis, which some people did, in our paper you can find the citation for a broader analysis that some other people did, but we're just going to use a couple much simpler models to illustrate the workflow. And the first step really is just looking at the data. And so you're probably all familiar with a plot like this. It's just a scatter plot of the satellite measurements and the ground monitor measurements for the points where we have both. Right, and then the colors, I don't know if you can read the text, but are different regions. And these are regions as defined by the World Health Organization. And so that's just like, the R squared here is like 0.6 or something like that. It's a decent linear trend, but we can kind of see already that there's probably some variation by region, right? So these are the World Health Organization regions on the left. But then you could also say, well, why do we need to use those? You could also come up with regions based on maybe clustering on the thing that we care about, which is in this case is the PM 2.5 concentration. The World Health Organization regions are just geographically based, except for one region which just counts wealthy countries, which is the pink on the left. So Australia and the US are in the same region in that model. And then we could do the same thing, but like just put down different regression lines, and right we get different lines here, right? And so these aren't like, we're not interpreting these things too much. This is just kind of looking at the data a little bit, seeing some trends here and saying, well, there's different ways we could think about this. And really, we've already come up with 3 potential models, right? One is just a simple linear regression, not hierarchical, 1 slope, 1 intercept here, where on the left, when I put PM 2.5, I'm referring to the actual ground monitor data, which we're basically taking as the truth, although it's maybe slightly noisy, but it's really high quality data. What we want to do is basically figure out if we can calibrate the satellite measurements better based on learning about the relationship between those and the actual ground monitor measurements, right? But we also had 2 other models I just mentioned, which are really the same model but with different region groupings, right? Where we have a hierarchical model with slopes and intercepts that have shifts based on which region you're in. And so the 2 models here are the World Health Organization region groupings and then the other region groupings. And then, of course, we have some priors here. So this is like a pretty standard model with varying slopes and intercepts. The actual models that the other authors who did a serious analysis of this problem used were a little more complicated. All right. And so that's the exploratory data analysis. Prior predictive checking is where we say, okay, what data does our model generate, right? Not what data are we giving to our model, but if we write down the model and we simulate from it, what data does that generate, and is it at all reasonable, right? And so Dan made this nice slide, which I think is the way that we're thinking about this is that we're really committing to having a joint model of everything that's observed and everything that's unobserved here. And we can decompose that in different ways. The one in the middle is more useful, seeing as it's the whole point is to calculate things like the ones on the right. But we're thinking about this joint model that we can use to simulate data, right? Fake data, if we have a joint model of the unknowns and the observed, right? And so to do that, right, so, well, first of all, you need to not have an improper prior, right? But if you don't, then you have a nice way of actually simulating from the prior data generating mechanism, which is to sample the parameters from your prior, sample some fake data from the data generating process given the parameters, and then the actual draws you get from that are realizations from the prior data generating mechanism, which is often hard to sample from directly, right? But this is a really easy way to do it. And so why is this useful? Well, it's because you actually have to think about what are the implications for the choices that you're making before you fit the model. And so it's been pretty standard for a long time for people to be skeptical of using informative priors. But what happens if you use kind of standard non-informative priors in a model like this? So these are kind of, there's other things you could do, but these are traditional in the literature kind of non-informative priors. I'm using standard deviation here instead of variance for the normals, but, and we get simulated data like this. So the x-axis is the observed ground monitor measurements, and the y-axis are simulations from the model before we fit it to the data, right? Just from our prior data generating process. And we have some issues here where right, the data that we can generate from our prior, right, is 2 orders of magnitude different, and that's on the log scale, right? So you couldn't, there's not even a spot on the y-axis here where you could put the density on the log scale of a neutron star, right? If these were the levels of particulate matter, we would not be in this room, we'd all be dead. And so what that means is that the data is going to have to overcome these priors, right? And unfortunately, in many cases like this one, the data is relatively hard to come by or sparse. We only have ground monitor measurements in a sparse network, right? And so, well, we could think a little bit ahead of time about what a more reasonable thing to do is without actually getting too informative, right? And so that would be to maybe have something like a 0 and 1 for our slope, our intercept and slope as our prior centered there, right? And then we get simulated data that looks like this, which is still much bigger than the actual observed data, but it includes basically all plausible data sets right here. We're not looking necessarily to capture any of the particularities of our observed data set, but we're saying, what are all the possible data sets that we could observe that would result in actual humans still being alive on Earth, basically, right? Using some domain expertise here before fitting the model, and if you plot them on the same graph, right, actually the better simulations look pretty weird because they're forced into this, down this bottom line here. And I'm gonna hand off to my co-author Dan to talk about the second half of our paper.
So one of the things we don't, hi, I'm Dan. One of the things we don't usually sort of talk about in the same breath as doing exploratory data analysis is actually the problem of making sure your model fits. And we don't really know whether it does. Like when we use MCMC in a Bayesian world, we don't really know if it fits. I mean, to use MCMC is to have deep experience with pre-asymptotics, which is a different way to say your model never converges. So we have some options. This is my personal favorite because it's a great thing. You can print out any page that has a trace plot on it and then pick it up, light a match, and burn it down. This tells you nothing. Yeah, I'm going to stick with that. This tells you nothing. There are various other things, but we really don't know what to do. We have all of these assumptions around certain types of plots, autocorrelation plots or various other types of things, but it's difficult to use. They tend to be univariate. As Jonah said before, we work on STAN, which is a version of Hamiltonian Monte Carlo that's just fancy. And our fancy Hamiltonian Monte Carlo does things that a lot of Hamiltonian Monte Carlo will do, which is it yells at you very loudly if it finds a problem in the parameter space. So this is the type of plot that does actually tell you something. The green lines and the green dots are when we've hit something called a divergence, which is basically when your MCMC proposal gets scared and runs away. So it moves down and down into the parameter space, goes, oh dear, and then wanders off over there. And we flag that because that's quite easy to tell. Ooh, well, that's exciting. You can tell here that they seem to be clustered around this bottom bit, or in the other plot, when we plot all of our coordinates in parallel, you can see that all of the green lines are going through this one point. And that is an indication that there is, in fact, something wrong with your model. So MCMC diagnostic plots can actually tell you about your model and your parameterization. They can also tell you that something has gone wrong, but we do need to think very carefully about clever plots for using MCMC, because I'm just going to throw it out there that a lot of the chains that we have staked something important on haven't necessarily worked as well as we would have hoped. If I could move to the next slide, that would be wonderful. There we are. So that is one thing that we can look at with visualization, and that should be a part of our model checks. We do this with fake data, we do this with real data. Anytime we see an error, we ask ourselves where that came from. But once we've done that, we have some sort of inference, and we need to see whether that sort of inference actually made any sense. And there are some arguments over how you should do this, but one possibility is to say that a good statistical model that has been successfully fit and successfully explains the data should also be able to successfully predict the data. So we use our posterior predictive distribution. This is different to the distribution that Jonah was talking about, which was the prior predictive distribution, because we like, consonants. We like the harsh P sounds. So our posterior predictive distribution, which will sound great on video, is here, and we basically take our data generating mechanism, P of y given theta, or our likelihood, and we average it over all of the parameter states theta that are consistent with the data, which is one way of interpreting the posterior distribution. And we can look at things. So for instance, we can take a look at what comes out of that. This is a very simple plot that we can always do. Look at our posterior median across groups. That's the solid line. And, look at our distribution for the posterior median. Okay, it's a functional, we can get a distribution. And look at where it lies compared to the actual data. And you can see that model 1 doesn't seem to be particularly well adapted, and model whatever that is 2 might be better. Now this is a problematic thing because of course we're using the data to check the data. So this is not a formal diagnosis, but it is a thing that you can look at, critically assess, and have a cup of tea and think about what you've done. Which I think is a lot of practical statistics. It's getting the data into R and then having lots of cups of tea. A different option is to take a look at, try and get these information criterion type things. And we're at a red paper meeting, so we can't not talk about the DIC. Although if we could not talk about the DIC, we would not talk about the DIC. Because, yeah. So we have, I'm sorry, I saw Les Mis on the weekend and I'm feeling very dramatic. Right, so one thing that we can use though is these predictive distributions. So the densities of these, so the log predictive distributions can be actually quite useful for us. In particular, they are useful to make a score, but the score isn't really that interesting to me. What is interesting to me is this plot. I have 2 models and I am putting the difference for each point of the expected log predictive distribution. Okay, and you can see some stuff going on here. For instance, in that ugly green region, it seems like model 2 is doing better than model 1, whereas in the ugly region on the right, model 1 seems to be doing better than model 2. Okay, so you can capture some inhomogeneity in how your models fit, and you can use this to build the next step in your network of models. Because our aim should never be to say that this is our final model because I am genius. It should be to say what is the problem and what can come next, and this is the type of plot that can be useful for that. A different thing that we can do is we can take a look at just how similar distributions are, predictive distributions are, to the ones that you would get if you left out a data point. This k-hat thing is essentially a tail index of a Pareto distribution, so it tells you how weird it is. And a lot of these points are doing good, some of them are a bit exciting. That one over there, 2674, is very highly influential. This is essentially a leverage plot, but for complicated models. That's Mongolia. So that's essentially the point of our talk. Visualization is an invaluable way of justifying and criticizing our inferences. We can't leave it behind. The thing that we should always remember is linear regression. People sat down and worked out how you can use the plots and the diagnostics for linear regression to actually work out what is wrong with a model, to make critical model judgments. We need to be able to do that for the complicated models that we are now recommending that people routinely fit. We can't do that. So we either need to stop recommending that people routinely fit them, or we need to get better quicker at actually helping them diagnose their problems. So remember, look at your data, look at your model implications. Pictures and fear. This is the way that we do this. We draw pictures and we have fear. Or we inspire fear, or both. It is important to look at your computational diagnostics. This is Bayesian because we do Bayesian stuff. It is equally true in likelihood-based settings or estimator function-based settings that your numerical method has a tendency not to work as well as you think it does when your model is complicated. There is literally no excuse not to look. Hope has no place in statistics. So stop hoping. It is important to look at the implications of your posterior. What is it actually telling you? Are you seeing some weird features from your prior jumping through because there are elements of your model space that are not completely constrained by your data? And as you see more complicated and more singular models, this is often the case. Because in the end, we don't have good theory for almost anything that we do in practical statistics. And I have a very sort of strident definition of good. I don't really care about asymptotics unless we've set something to infinity, because pre-asymptotic behavior is everywhere in complex models. So without good theory, what do we have left? We have brain work, we have pictures, and fear. So use your fear. And I'll just leave it on this slide for a couple of other things we've done since this paper has been written. Thank you very much.